Welcome to this second lecture, and over here we're gonna cover a little bit more about variables, about expressions, and also we're gonna dive a little bit deeper into two nodes, especially the for loop and the copy sub. And these two nodes are going to help us for a very great deal into creating procedural content. Now, before we start, let me give you a small introduction, and it's something that we're going to practice along the way. It's not something we're going to do immediately in this lecture, but it's going to show you what's the power of it and how we can apply it. So, Greeble and Ernie's, first of all, what is it in fact? Now, I have a few examples over here of some old sci-fi movies and some more recent ones. Greeble and Ernie's, those are all those little details that you see on the spacecraft, and those are there just to give you the impression of size of such a craft, of such a vehicle. So it's all this detailing, all this kind of work that gives you the idea that we're talking over here about a very big spaceship. We see that the same over here. So it defines a little bit the size of the whole thing. Right here we see it as well. You can see it, the spaceship is much smaller, so the amount of detail becomes also less. Here we have like bigger ones such as the Borg cube, and over here like this enormous UFO which is like almost covering the whole city, showing you all this detail. And the reason why we recognize this as being size, that we are also confronted with all those things in real life. For example, we see over here like the Manhattan part of New York. This is showing you more or less the same kind of structure. So you have like a lot of very small detail looking as a very complex structure. So what we want to do, we want to have the computer doing at least a lot of work for us. Now, as an example, I've created over here in Houdini is a tool to create a very simple set of Greeble and Ernie's. And so the only thing I need to do is first I need to just bring in like a very simple surface, as you can see over here, and then just with the operation that I've created in one step, it turns it in something like this, which shows you all kinds of detailing as if it's like this very mechanical complex thing. Now this is just a very simple prototype, so as you can see, if you look deeper onto that, all those shapes are just like very simple representations, but you can go much further than that and actually create like vents and little machinery, all those kinds of details, which would make it like very convincing. Now, to show you again another example of what is done in CG, I have this site over here. It's a guy under the name of Fractal Sponge, and you really should take a look at his work because it's really amazing. But it's also just the one person that I know that can do something like that, because this work is so big, it would demand so much time and so much effort to create something like that, that I think there are better ways to approach at least parts of it. Now, as you can see, the detailing over here, we see like all these panels, we see guns, and we see like very detailed things. Some of the things are simply not possible to just do automatically, or at least in a very easy way to place them automatically. But a lot of those things are, and then we're talking about like details such as we see over here, or other little greebleish things, but not the guns, but also like these panels over here. Now, let me show you quickly a few examples of this. This is like a big size render, and so to give you an idea of what kind of shapes we're talking about, you see this is like quite a very big model what this person is building. Now still, apart from the side that there's a lot of repetition and that he can work with a lot of instances, still this is just a real amazing piece of work. Now I will go into some other details. So you see over here the bridge, So if we zoom in on parts of this, now you can see over here how extremely detailed this model is. Also, like all these little guns, everything is just extremely detailed. And we see it over here, the bridge, even like the very small windows, all those things, they've been detailed to an enormous extent. And so again, the last picture showing you the whole ship. So this is again amazing work, but what we will try to do is to see how we can use several ways, or that you can learn how to make procedures that would help you in a very big deal solving problems such as these. Okay, so the very first things that we're gonna do is we're gonna start over with what I've shown you in the very first lecture. Is we're gonna stack a set of boxes, and so we're gonna repeat just exactly what we did before. Then we're gonna use a stamp, or we're gonna do it with a for loop so that we can do the stacking of boxes in an automatic way. And I'm gonna show you just a few things that you can play with and that you can experiment with. I will always take a little short pause, and best is when I take this little pause, I will explain to you what you should try to solve on your own. So try to solve it, and if you didn't solve it, or if you did solve it, you can continue with the video and see what you need to do or how you should have done that. Okay, so we're gonna start with it with creating stacking boxes. So I have this empty view. I'm gonna create now a little basic graph, and I'm gonna come back immediately to you. Okay, so I created like an empty object, and within that empty object I created two boxes with two transforms and a merge. So the idea is that the first box is going to rest on the ground, and that the second box is going to rest on top of the first box. Now the thing which is important to know is that the system should be as flexible as the following. You should be able to add, for example, a transform node in here, in which I'll be able to adjust the scaling of one of those boxes. So independent of what kind of transformations you do over here, this system, this transform, should make sure that at always the box is resting on the ground. So try to solve this, and when you've solved this, and pause the video right now, and so when you solved it, you can come back and see what's going on. Okay, so let me show you how to do something like this. First of all, we have this first box, and it needs to be resting on the ground. We have a transformation over here which is changing the scale, so that doesn't matter. It doesn't matter where it's placed, so I'm gonna change as well the placement. Press enter just to make sure that I have like the view, and like that I can make it visible, such as this. Okay, now what do I need to make sure that it's resting on the ground? Is first of all, I need to get the bounding box information of this object. So even if this would be an irregular form, that you have only one point as being the lowest point, I just want that one point just to rest on the ground. So for that, what we're gonna get is we're gonna try to get the bounding box information of this. Now something which is very important to remember is that we're working over here in compound space. So it's not that you have an axis inside in which the object is displaced, it's just you have like the position of points in world space. Now if we want to get a bounding box, you can get like the following information, and let me show that to you what we have over here. So creating stackable geometry, I'm gonna skip through a few things, and we're gonna need some variables. So just a little bit further. The variables that we need like one of these set of variables, and we're talking about the bounding box. So we have like the y max value, the y min value, x min value, x max value. You have that also in the z direction, as you can see in world space over here. Z direction, you have like Z max and Z minus. So these are showing you in world space where the boundaries are of this shape. Now you have also the centroid, CEX, CEI and CEZ. So these are giving you the center of the object, as you can see over here, like with these lines. And then the third set of the information that you can get from the bounding box is the size. So that's just like the length over here of the object and the width, the length, the width, and the height of the object. So it's one of these things that we need to use. Now, in order to make sure that we're able to place this object on the ground, we need to see, okay, how high is it above the ground? So if you measure this, then you know it's the lowest point that you need to measure. So it's the y minimum value. And this is the variable that we're going to use. So let me just type this in, $y minus. Now if we do this, then we see the object jumping up exactly the y minus value. So the y minus value is the lowest point over here from the ground. And so we do this, then we transform the object by, again, this value. Now to get it on the ground, it's very simple. What you need to do is, of course, instead of just adding that value, you need to subtract that value. And so when subtracted, you will see everything will be placed on the ground again. So that's the idea, the first thing. Now, we're using variables over here. Now, what are variables? Let me go back over here to our presentation. First of all, let me see if I can get to the beginning. Variables, first of all, what is important to know is variables get their information directly from the node itself or from the connected node. Now in this case, when we try to get bounding box information, we get it directly from the node above. So it's trying to get information from the connected node. And that's the difference also between expressions. Expressions allow you to get information from totally different nodes, nodes which are not connected at all. So this link that you see over here is the expression link. So you have over here an expression for the bounding box information, getting information from something unrelated, and a variable getting information from the related thing. So the types of variables that you have local standard or standard variables. In fact, I should make them more as a whole. Perhaps it's best to look at them as being local variables. And then you have like global variables. Now the difference is local variables, they get their information from their parent nodes or from themselves, like I just said before. Global variables are variables which are available from other parts. For example, you have things like the timeline, which is $f, or the variable of the number pi, etc. So if you have like variables which are globally from the whole system accessible everywhere, and you have like a local variables which are most of the time used actually only within geometry, but which are accessible from the node itself or the node above. Now there are a few things which are important to know. Is variables always start with a $sign, and variables are always written in capital letters. Now you will see when you have written your variables in a correct way or on the proper position, the variable will turn green. If there is something wrong, the variable will turn red. Now this is not a waterproof system. Sometimes it can be that your variable will show up red, but is still able to work because the system doesn't recognize it immediately. So it's some kind of a help, some kind of a guideline to help you through, but it's not like a 100% foolproof thing. Okay, Now again, the thing which is very important to know is that a variable is actually nothing more than a shortcut for an expression. So you can do exactly the same thing with expression, but a variable just makes it much simpler and faster to access. Now where can you find them? You'll find them always over here on the help file from the node itself you have selected. For example, if you have a transform node, you select the help file, you find over here local variables. You will see over here there's like this blue shortcuts to get to the right parts of your help file, and you will find over there local variables, and here they will explain to you what those are, what those naming conventions are, and what they can do for you. So the very first thing, like we explained, is how to get a box right. That's something that we did, and we placed it on the ground. So if you're gonna look over here, our box right now is resting on the ground. So that's the first part that we've completed. Now the second part, we need to get the second box stacked on top of this one. Now in order to do that properly, we need to do first one thing. First of all, we need to make sure that also this box is resting on the ground. And the reason for that is that if this box is resting on the ground, the only thing we need to do then is to measure over here the height, or the maximum height we have over here, and then we can just add it together with the box which is already resting on the ground. So let's do that first. We do exactly the same as with the first node, y minus, so the minus value of y. In this case, since it was just right in the middle, we have like a negative minus value, so that's minus a half. And if we negate a negation, we get a double negation, so it becomes positive. So minus a half becomes plus a half, and so it will be moved up. So okay, so we have these two parts, and we need to get now an expression in order to stack it on top of this. Again, why we need an expression? Because with a variable we can only reach what's inside or what's on top over here, but we need information from this part. So what we'll do is we add a bounding box, then we'll go to this node, double point slash, and we can select the node. So we're not going to select it over here because right here we didn't have the transformation. The box is still standing in the middle. This is a transformation, but a random transformation, also something we can't use. This is the one which is like completely corrected, the shape, which makes sure that it rests on the ground. So we need to get our information from this one. So that is xform1. Now it's always important that we again close our brackets over here. We have a comma. And now the float type, something I'm going to explain you later when dealing with expressions, the underscore y max. In this case y max, because we want to have the maximum height value over here. So we're measuring the maximum value of the y direction, which is these points over here. So we get these numbers added, and if we merge them together, we see this box is stacked on top of the other. So if I take this box over here and I will start playing around with scaling, as you can see, the other box is always automatically being stacked on top of the other one. Okay, so expressions. As you could see, I used this little expression over here. So let me go back, show over here the expression. So we have first the expression name within two brackets, and then all the information that we need for the expression to make it work. So how does this work? Well, let me explain to you a few things. First of all, we have an expression, and I'm gonna take like a point expression, which is also an existing expression, as an example. Now, a point expression allows you to get attributes from certain points of geometry. I will explain to you what attributes means and what points means and all those things. So we're gonna go over here step by step. So imagine that this node over here wants to get point information from this node over there. So we take the expression point, and what we get from the help file, and that's really important that you can understand what's going on over here, is we see in the help file we get surface node, comma, point number, comma, attribute, comma, index. Okay, so we're going to start by trying to understand what all this means. Now, if we go back to Houdini, and let's type it in over here, for example, point, now you will see you get also like this little help file if you stop. Now you see the following things: string, surface node, float, point number, string, attribute, float, index. So what they're doing over here is they are explaining what the property is looking like, what's being asked over here. So we need a surface node, and to find the surface node you have to write it down as a string. If you want to have the point number, you get it as a float, so this is a number. If you want to know the attribute, again, that's the name of an attribute, so that's a string again, and so on. So you have multiple things. Now the very first thing which is important to know about this is that strings are always typed by double quotes. So string needs to be always in double quotes. So if you go back to what we have over here, let me just remove the expression over here, then you can see we have defined over here the path of the node, and indeed that's correct, it is between two quotes. Now this is important to know that each time you have a comma, it's asking for something different, as you can see over here. So you have to make sure that you always close before the comma starts. So you can see that over here. Here we would have like double quote right over here and double quote right over here, always before the commas. So defining the path. So what we need to do is we need to try and find where we can find this node. Now there are two ways. You have an absolute path where the node is located, or a relative path where is the node located in relation to the node with the expression. Now to explain you the difference, you can see that actually with your colleagues in class. For example, you're in your classroom and you want to get some attributes or some properties from a colleague within your class. For example, the color of his or her hair. So what you could do, in order to find that person, you could use an absolute path. What would be an absolute path? An absolute path would be like, we start off in the galaxy, we have the Milky Way. In the Milky Way we have a planet called Earth. On that planet Earth there's a country Holland. On that country Holland there's a city Breda. Then we have like the street, we have the pack house, we have the classroom, and if you have run through all of these, then you have the name of the person. And that's defining like a real absolute path to that person. So you know how to get that attribute. Now a problem with absolute paths is if you make changes, then the absolute path doesn't work anymore. For example, something very simple. If you guys change on a later hour from class, you change from one class to another, then the first absolute path is not valid anymore. So all the first things like the Milky Way, etc., until the pack house building is still correct. But let's say the room 007 is not correct anymore because you as a group has moved to room 2006, for example. And so there's a better way to find the path, and that is a relative path. And like I said over here, a relative path is relative to the node where it is, where the expression is. So you can compare that the same. You have to get your information from a colleague. So your colleague is sitting always in the same class as you. So you can say just his name. And if you move to a different class, again, just having his name is the only valid thing that you need, because it's relative to you. He's always sitting in the same classroom. So that's the important difference. Now, about these two signs, what we see over here, it's something important that you need to know. These are symbols how to get to something. So this is quite clear what it is. obj/geo/box. So it's a little bit like a path that you follow going in folders. For example, you go in the folder obj, then you go in the folder geo, and then you find the box over here. Now the double point and backslash, what they mean is go one parent up. Now this is important to know. Why would you go one parent up? Because why wouldn't you just use a name? We're talking about like this box or something else. So if in the case over here, why shouldn't we just write down like this, x form 1? Because yeah, we're right over here. Now the thing is, if you're inside a node such as this, the idea behind it is if you would write directly a name right here, you would have like access immediately to all the channels which are inside over here. This is how it works. Now, if you want to get information from a node, you first need to get out of the node, so you have to go one parent up, and then you're in this space where you can select exactly the node that you want. So if you want to get higher, for example, if you want to go to object level and imagine that there's a camera, you have to go one up again. And so now we're at the object level. And so this is how you can go up or can go deeper. So that's the very first part. We have the expression, then we have the location of our node, comma. So now the next one. It's asking for this expression, the point number. Now how can you see the point number? Well, if you have like a box or a shape, it has been built up out of several points. Points are the names that are given in Houdini to vertices in Maya. So it's really important to remember, in Houdini we're talking about points. Now each one of those points has like an index number. They're numbered. They start up from 0 and they count up the more points you have. So if you want to get a specific point, you can see, okay, let's select point 3, and then we're going to retrieve the information which is attached to point 3 over here. So get first the node, and then which point on that node. Now we're going to get the information, what kind of information we want to have, and that's the attribute. Now points can have many attributes, as can polygons have many attributes, as can vertices have many attributes, and as can objects themselves can have many attributes. Now, what is an attribute? An attribute is something which has a name and that can carry data. For example, a point has like a set of attributes which are necessary in order for it to be there, and a set of attributes which are like something that you can add. For example, one of the attributes for a point to be like really necessary is a position attribute. So without a position, the point wouldn't have like any place in space. So that's one that needs to be there. But there are other ones which are not so necessary, but which are recognized immediately by the system. For example, you have a color attribute, or a normal attribute, or a weight attribute, like the tree we see over here. But you can add as many attributes as you want. Custom attribute 1, custom attribute 2, 3, you can name them whatever you want. And you can compare this actually a little bit with this girl you see with bags. So this girl would represent in fact a point or a polygon in Houdini, and a point can carry like many bags, and these bags are in fact the attribute names. So for example, you could see this bag would be named color, this bag would be named normal, this bag could be named weight, and each one of these bags can carry its own value. So each point can have like all these kind of bags, and each one can have their own unique value inside. And this is very important because you can do lots of things with it. Now give me an example of what kind of an attribute could be useful. For example, you could create a distance attribute. So you give it the name distance, and the reason why you give it the name distance is, for example, just to make it easy for you to remember what that value inside of it means. Now, if you have like a set of points over a surface, for example, you have a road floating over a surface and that road is made out of several points, you can measure the distance towards the ground. So each of those points would have like a different distance value, and then you can read out by using the expression we were working with, the point expression. You could read out each point's distance value and then use that value to make sure that each box is going to be long enough. So, what's also important to know about attributes. Now, attributes, they can be like lots of things. An attribute can be a value of one thing, and so like a distance is just one value, but can also be a value consisting out of three things. For example, it can be a vector. For example, you could store color inside an attribute, and color consists out, as you know, of RGB, red, green and blue. So in that case, an attribute stores like a float value of three different values. You have also string values, so an attribute can contain text as well. So those are the things that you can all add into attributes. Now if you want to see what kind of attributes are there, the thing that you can do is middle click on the node and you can see the attributes being created. You see them right over here. So I created with the attribute create one attribute called hub Holland hub, and it consists out of three values. It's a vector, as you can see. This is one created, it's containing a vector, and a vector consists always out of three values. It has also one detail attribute, a variation map, which is there by default. Now right here I've added a link of a list of well-known attributes. So it's very worth to check that, because using attributes like this, Houdini can most of the time immediately use them. So check those out. Now, since Houdini is already a very old program, I believe it started in 1995, so that might be very close to when you were a very, very little kid. There have been growing in some inconsistencies on how attributes and variables are being created. So this link, it's like a big talk on those topics, and it shows you in great detail what all the issues are with it. So make sure to check that out. So that's a little bit about attributes. Now, like I said, is we need to get in this case I added as an attribute, for example, the color. We want to get a color of 0.3, and like I said, an attribute when it's created out of colors, it consists out of three values, R, G and B. Now that's the last part which you're going to use, is the index. It's going to specify exactly which channel that you want to read out. For example, do you want to know the red color, the green color or the blue color? So the index of the color channels is as follows. First one is named or is index 0, the second one is index 1, third one is index 2. So it continues all the way like that. And so if you want to get like the green channel, you have to put in index 1. So if you look at it as like this big overview, the thing what you have with an expression is an expression will retrieve information for you. And so what you will do with this expression is you're going to specify like multiple things. You're first going to narrow down to where your information exactly is coming from. So in this case, we start off with the surface node. In that surface node, we have this object and we try to get the point. Then from this point, we're trying to get like the right attribute out of the whole list it can contain. And then from that attribute, we're gonna specify which part of the attribute exactly that we're gonna have it. So this is this whole path narrowing down so that we get exactly the thing what we need. And this is how expressions are working. So if we go back over here to our bounding box, we see right here we have narrowed down to the node itself. We don't need much more information because we're talking about the bounding box information, which is like the whole thing. So we don't need to have like a specific point number, or we don't need to have like a specific attribute. All the rest is known then. Now over here, if you see it in the help, if you go back, you see this is up. Let me delete this. We see over here, this is also saying type. Now the thing is, with type, I can add also a number over here. So it doesn't matter. The number is going to work, although it's going to give me a result that I don't know what's going to be like. And I will show you how it relates. So if you go back to the help file, let's open up the help file over here, go a bit faster. And I'm going to the root of Houdini over here, go down to the expression functions. You will find right here bounding box expression. Now here you can see the type can be one of these. Now we see here a whole list of types, and what they've done over here is they have actually named those types, and that's very important. The reason why they named it is because like this you can easily remember what there should be in. If it was a number, then it would be much harder to remember. Now in order to make sure that this box, like we had before, is standing on top of this, we need to use the dy max value. So again, we can do the same thing with normal type. So this is index 0, 0, 1, 2, 3, 4. So we need index 4 in order to get this function. So let's try that, and let's prove immediately that this works. And as you can see, this just works perfectly. So this is exactly the same as dy_y max. Okay, so I hope this clears things up quite a bit. Now we're gonna continue. We're gonna start with something else. We're gonna start with creating a for loop, because we want to do the following thing, and this is going to be explained a little bit later. So we have like several boxes over here. Now imagine that you want to stack like multiple boxes on top of each other. Let's say that we want to stack about 20 boxes on top of each other. Well, this is something that you want to do, that you don't want to do by hand. So in principle, what you could do is do something like this, copy this and paste it all along several times, and then have all these things like connected to each other. And if we do something like this, we could say each time we're gonna get the bounding box information just a little bit further. So this one gets of 2, this one from the previous one, which is 4 over here, and this one is going to be 5, and this one is going to be 6, and so on. But as you can see, this is not very flexible. Although it works, again, every time I need to change something, well, it doesn't work 100% correctly. Yeah, because I'm scaling over here. I shouldn't be scaling over here. By the way, this is something which can be fixed, but I'm not going to show this to you right now. But imagine if I have a transform node right here. What I can do is to scale that transform and size this object, and as you can see, everything will follow as well. But what we want to do is we're going to make a system which allows us to do it just in one go automatically, and for that we're going to use a for loop. So for now I'm just going to delete everything we have over here, and I'm going to start over new just simply by using a for loop. So press tab, a for each loop. So what is a for each going to do for us? A for each is going to repeat an action several times over and again. And it's able to store and collect the results of that. So there are many ways how you can do a for loop. We can do for loop for each group. We can do it for each attribute value. We can do it for each number. We can do it for each primitive point. Now I'm not going to go over these three. Each group, attribute value, and primitive point I'm going to ignore for now. We're going to start over here with each number. Just going to take it very simple. Now, the thing that we have is we have like a very simple thing. We have like a number range. We start from 1, we go to 10. So this means that we're going to iterate 10 times. And we can see that over here we have an increase value by 1. So to look at this is in fact a range going from 1 to 10 by steps of 1. So if we do it by steps of 2, then we go from 1 to 10 with steps of 2. That would be 5 iterations. This would be 10 iterations. So that's important to remember. Something we see over here, that's an index stamp name. So again, it's a little bit similar to a variable, although it's not the same. It's a stamping name, but you can give it whatever name that you like. So blah blah would be a very valid name, except the only problem with this is it's not very recognizable for you. But just to show you that it's just whatever name you add over here. Now, what is a stamp name? A stamp name or a stamp is an expression, and you can see it as a stamp of an office worker. So when he's stamping letters, he can stamp each letter just with a different number, and this is exactly the same thing what it's going to do. So each iteration is going to keep the number where it is. So first iteration is number 1, second is number 2, third is number 3, and so on, goes on and on. So you have each time a unique number. And so the index stamp name is going to return you the number of the iteration you're at. And that's something very useful, especially if we want to work with random values, etc. But that's something for later. So let's start first. First thing that we have an input to detect groups and attributes from. This one needs to be connected at all times. The other ports are extra ports that you can use to add extra information in. So we're going to connect now the node over here and over here. Now it's important to know the for each node is a special node. You see it's blue, and when it's blue this means that you're allowed to get inside of this node. So if you press Y or double click it, you go inside of this node, and you can see it over here as well. In a directory we are inside of the for each. Now by default we have this node over here, the each node. And the each node is just important to remember, because this one is going to keep what has been going on. So for example, what we want to do with these boxes, we want to stack a box on top of this box, and then a box on top of both of those boxes, and then a box again on that result. So we're going to stack each time on the result, and this one is able to keep the result each time you do an iteration. So once you have put a box onto this box, it goes back in for each node and it stores it over here, and then you can stack a box on top of that result. You merge it together, it gets stored again over here, and you can stack a box over here. Now you see right here we have these input ports. You see also they have been connected to the box. We can see that right inside. So what we're going to do first is we're going to add a transform node, and you will have to do exactly the same as what you did previously. So first things is make sure that this box is resting on the ground and that the box is going to be placed on top of the each node. So I'm going to pause over here and try to write down the expression yourself. Okay, so the expression to be used, and the variable is minus $y minus plus bounding box, get to the node that we want to have, the each one, close brackets, d underscore y max, close brackets. And so this one is being stacked on top of the other one. We merge them both together. And we see one box is being stacked on top of the other. So let's go up. Now we have done 10 iterations, but we still don't see like a special result. Now if you select with the middle mouse button, you can see the number of iterations for last cook. It has done 10 iterations, but still we see only 2 boxes. But do we really see 2 boxes? If we look at it and we check, for example, the point numbers, you will see we have many points on top of each other. Same with the surfaces. So in fact it's just like this setup, like one box stacked on top of the other 10 times over. So this is really important to know. And that has to do with the following: merge results. If this is switched on, what the for each loop is going to do is it's going to execute what's going on over here. So we have like the box coming in and this box being placed on top of it, and it's going to store that result and then do it over again for the second time. A box, stack a box on top of it, keep the result. Box, stack a box on top of it, keep the result. So it has like 10 times the same result because we didn't change anything. So what we can do is we can switch this off, merge result. Once we do this, then it's going to keep the result, but it's going to stack a box on top of the previous result. So switch this off and suddenly we see all these boxes stacked on top of each other. And so it's very easy. You can increase the numbers over here, and the more you increase it or the more you lower it, the more boxes you have stacked on top of each other or not. Okay, so this is a very simple thing. Now let's go inside, and I want to show you something about viewports as well, which is important. So go inside, use the transform node, and so what you can do is we can, for example, rotate the box. But as you see, what's going on over here is that only the last box is actually rotating. And that's kind of strange because we're doing this rotation as far as I can see it on everything. Now the problem is as follows. We are inside right now in this for each node. And so it's not going to show the result of the total iteration. It's going to show you one iteration. And the thing we're interested in, and that's going to show up when we go back up, is that if we go out and we see it on this level, then we see like the total result again. So how can we get something like this? Well, that's the following. We can pin our viewport on this level that we're working on at right now. So this is important. Make sure that you're outside of the for each node so you can see it, and then pin your viewport. Once you do that and you go back inside, you can start playing around with these values. Now you will see you won't have like the controller anymore, but you can work with the virtual slider, and you'll see that now everything starts updating properly as you would expect. So this is a way how to figure that out. Okay. But now we want to go just a little bit further. And for that I'm going to use a special expression which is called the stamp expression. Again, look it up inside the help file of expressions. I've shown you before in a video where you can find your expressions. So if you try to look up the stamp expression, you will find exactly what you need over there. Now I'm gonna go just a little bit further over here to this expression so I can explain to you what's going on. So first of all, the stamp expression, what does it say? It says scope, token and value. Now they talk about scope over here because it's not only working within surface nodes. It's an expression that can be used in various places. So scope is different, but scope means actually the node that you want to use. Now the color codes that I've added over here, they don't match up what you see over here, so it's a little bit confusing. These colors are matching up with the boxes that you see over here. These colors just match up what you want to see over here. So the node that you want to use is the scope. Token is the stamp name. You can give it a name like I said, and the value to be used if the token cannot be found. So if this name cannot be found, perhaps it just doesn't exist, then it's going to use a default value that you put over here. So the stamp name is this one, the token. So let's go inside and let's do something special. What I'm gonna do is I'm going to randomize the size of these boxes. So I'm gonna make like random changes, make them bigger, make them smaller. Now before we can continue with that, it's important for me to explain you a little bit what random is. So randomness, first of all, you need to know that in a computer, randomness is deterministic random. This means that in fact it gives you always the same result, but it feels like random because we can't predict as a human what's going on. But for the computer, it's just going to result in always the same thing. So let me explain to you what it in fact is. Randomness is in fact some kind of curve, an animation curve, which has been procedurally generated. Now the seed number you see over here is something which is going to take a sample of that animation curve. So I've drawn this over here, and this might explain you what's going on. So a random curve looks something like this. You have like different kinds of curves. You have like a Perlin curve. You have all kinds of different methodologies to create something which is more or less random. You have like noise, different types. Now this thing which is generated follows just a set of rules. It's let's say it's a combination of a lot of sinuses and cosinuses. So each time you use it, this curve is going to remain exactly the same. Now the seed value is actually, like I said, taking the sample. So if you show this on this curve, and I've made a few examples of that, if you type in random 9 as a seed, it will return you a value of 0.1. So it's like in an animation taking a sample over here. If you do a random of C12, it's going to take a sample over here, and you're going to get this value, 25, and so on. So as you can see, it's in fact just the same like as in an animation. So imagine if this would be time. With the time slider, you would also sample something of what an animation curve is. The only thing which is also important to know is that the random value will also only return you a value between 0 and 1. So it doesn't make overshoots. It's always clamped in those things. So if you want to make sure that you have like a wide range, the only thing you need to do is, for example, get like this random value and you want to have it from 0 to 5. Then you do just a random with seed value, and then this whole you multiply by 5. Okay, so let's go back and see what we can do over here. So what we're going to do is we're going to change what's in here. And I explained to you what the stamp function is, and now I explain to you what the random function is. So first of all, we're going to work here on the uniform scale, and we're going to type in this random expression, and also make sure to look that up. And as you can see, for example, if I use 2 as a value, you'll see this box is going to grow or going to get smaller. And if I slide around with it, you see the change. Now this viewport has been unpinned, so let me go back over here that we see this result, and let me pin it again, go back inside, and so now you will see much better what's going on. Okay, so there you see the randomness. Now, like I said, we want to have like randomness for each copy. Now, I was talking about the stamping function. So if you go up with the index stamp name, let me explain to you again. The stamp name is something that can be used by the stamp expression, and it's gonna keep each number in the iteration. So what we're gonna get over here is, for the first box, it's gonna get like random value of 1. The second box is gonna get random value of 2. Third box is gonna get random value of 3, and so on. So if we add inside of this node the stamp function, and let me just delete the previous bracket, we can go exactly to what we need. So we need to go up, and now we need to get the information for the for loop. Now we don't see it arriving right here. Now the for loop is actually the world we're in, the for each, so that's what we need. And if you want to reach that one, you just need to add 1 point. So what else? The string token, we named it blah blah, and then we have the float value. The float value when it can't find the token. So imagine if we have written a mistake over here, then we get like a value of 0. We close it, and as I select it over here, you can see that we've closed this one, but this one is still open, so we need to close that one as well. And now we have randomness for each box over here. Okay, now let me give you a challenge. We've created randomness for each one of these blocks, but what I want to have is that these boxes are not going to scale in all dimensions. I want them to scale in like separate dimensions, so you need to have like a randomness on the scale. Now you need to do something in order to make this randomness work on the scale for each direction differently. So try to figure this out and try to solve this. Okay, let me explain you what you need to do. I'm going to copy over here the whole expression because I don't want to write it again. Add the value of 1. I'm going to put it over here, again over here, and again over here. Now, since we have like the same expression over and over again, and it's again proof that the randomness is reacting each time the same way, and it's returning exactly the same values. You see it, they're also scaling like boxes. So how can we solve this? How can we make sure that everything becomes different? Well, it's the following. Now see, we have this expression nested within the randomness. So it starts off from 1, goes up to 10. Now, if I want to have like a different random set, what I need to do is, for example, make it start from a value of 20, going up to 30. So in order to do that, the only thing you need to do is within this, so that I'm going to add a value over here. So if I have the value of 1 and I want to make sure that it becomes 21, you just add it with 20. And since this is an expression giving me each time a new number, 1, 2, 3, 4, 5, it's 1 plus 20, 2 plus 20, 3 plus 20. That's being evaluated first within the randomness, and then the random noise will be generated. So as you will see, once we do that, we start seeing changes. Let me create another one over here, inside plus 50, to make another offset. And as you can see, we now have like totally different kinds of boxes, all with their own offset. Now you might have noticed that there is the first one who is not reacting. Well, there are different ways how to solve this. One way is the following, is that we're going to delete over here this box node. So we're going to delete by pattern. Right now it says exclamation mark star, so it means not everything, it's just the opposite of everything. So when it's deleted, what's going to happen is we have this box, the box is deleted, and we have an empty object going inside of here, so nothing. Go inside of the for each. The first step what's going to happen is we have nothing over here in the each. We have this box being transformed, being put onto the ground and being put on top of the each, but since the each is empty, contains nothing, it remains resting on the ground and is being merged. That's how we get our very first block. And then it goes back in here, goes back, we have this little block over here, a new block is being deformed and placed on top of that. And now we have like all kinds of random shapes. So again, if you want to play around with these values, you can just easily start changing those, and you see you get all kinds of random expressions. Okay, so this is how we deal with the for each loop. Right, the thing that we're going to do right now is we're going to use a node which is quite similar to the for each, and that's the copy node. The copy node is also able to use the stamping function. But before I go to that, let me go back to explain you one thing. Because what we've done over here is the nesting of expressions. And just to make clear to you what in fact it is, let me go back right here and let me show you what we have in here. So we have an expression, and randomness, it can contain a value. Now this value can be changed into, for example, another expression. So what's going to happen over here is that this expression is going to be evaluated first. So we take the bounding box for the sphere 1 dy max. This is going to generate a value which is going to be placed in a random function then, and then this one is going to be evaluated. So you can have like very complex ones, not that complex, but more complex than others. So if you round, fit, random, $pt, so the number, so each point plus stamp, etc., blah 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 blah. You can compare this a little bit to those Russian dolls. So you have each time an expression sitting inside of another expression. So this is how it gets evaluated. So first, the stamp value is going to be evaluated. That value is going to be placed inside over here. Then the randomness with this whole expression is going to be evaluated. That's going to generate a number. It's going to be placed inside of the fit. This one is going to be generated. You have a number inside over here, and that's going to be rounded. And then you have your end result. So this gives you a little bit the structure on how it looks. Now, if you want to have like a better view, a better overview of how this whole expression starts to look, you can always use Alt-E over a parameter, and that will open up a window so you can type it in a more, let's say, readable way. So, to come back, let's go to the copy node right now. And let's see it over here. I'm going to go back up. I'm going to switch this off, create a copy node. Now, the thing that we're going to do is the following. We're first going to create a grid, and we're going to use this same box. It doesn't matter really. I'm going to use a transform node. Now let's make it just separate, because otherwise it might be a bit confusing. Use a transform node and then a grid, and if you see it, well, we get, as we expected, like this grid with boxes. Right, so the first thing that we can do is, what I want to figure out is, for example, a way that we can grow the boxes all the time and that they get bigger and bigger and bigger, following the numbers of the grid. So if we see over here, if we follow the point numbers, we have a size of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and it goes back to 100. So what we can do over here in this copy node, we can use again local variables. So let's go to the help file and let's crash the computer. So I'm gonna pause over here and start over new. The good thing about the crash is that with a crash we can always show how to retrieve your file quite easily. Now you might have noticed that with the crash it showed you that it has saved some kind of a file. Now let me just open this file and you can find it very easy. You can find it always underneath the temp folder, and if you change it to last modified, you just have to go down completely, so you don't have to look for it or write down the number. Just accept and you will see we'll have a decent, properly written shape. So let's go back over here. Perhaps I go back to my floating points. Where was it? Yes, this is what I was doing using the build. So where was I? I had these boxes. I have this one over here. I wanted to go into the copy node, and there was where it crashed. So what I wanted to do is to create again a stamp. And oh yes, I used the help file over here. So what I want to know is what kind of a variable that I can use in order to retrieve the information that I want. So like all nodes, or like most nodes, let's put it this way, there are also for this copy node local variables. So you can select this one over here, and I would advise you to do that for all of them. So local variables, you can check it over here, and you see this whole long list of local variables. So what you need to do, I'm going to give you an example over here with $pt, the point number of the currently processed point. So this means that if you're going to have a look over here, that the point number of the current processed point, so it means it's going to copy this object on this point and it's going to return this number. So let's do that. Let's go to the stamp function and write down over here the variable that we need, $pt. So I'm gonna give it another name, copy, which is the name I mostly use all the time, and then we're gonna stamp the inputs. This is important. If you forget to use this, then your stamp function is not going to work, and this is something that often happens in the beginning. It happened with me, it happened with other students, so it probably will happen with you as well. So always try to remember this and check this. So now we're gonna use the stamp function, and I'm gonna use it over here in the uniform scale. So stamp. Again, what we need to do, like it says over here, is string scope. Now the scoping for the stamp function means trying to find a node. So this copy one, we're gonna get the information out of this one. And before when we were working inside the for each, we got the stamp information from this node. So now we try to get it over here. Copy one. Now the string token, so the name that we have given to we've given to the stamp, and then the value of the stamp token cannot be found. So 0, or perhaps let's just for fun use number 2, because that will show it to you when it doesn't work. So if we're going to see this result, we get suddenly a white screen. Now what has happened? Well, let me show you what's going on over here. We have this grid, we have these numbers. These numbers are being read out by this copy node, and are being stamped over here in uniform scale. Now the problem is that 0, that's okay. So a scale of 0 is an object which is very small. 1 is the size of 1, 2 is double the size, 3 is 3 times the size, but 99, it means that this object is being made like extremely big. So what we can do best in order to make sure that it looks a bit smaller is, for example, multiplied by 0.1. If you're gonna have a look at this, you can see that we have for each point like this increasing, growing size of objects. This is something that you can use. Let's go a little bit further. Let's do something else, and what we're gonna do is we're gonna make something which looks more or less like we have been painting on some kind of an object. So that the places that we're painting on, that their boxes are going to grow. So first of all, I'm gonna add a color. The reason is I want to start off with a black surface. So the color is black. You will probably need to set it to black yourself. The reason why it's black over here from the start is because I made black as a permanent default. So it's perhaps something you can do as well, because most of the time when I need a color, it needs to be black from the start. Okay, so the second thing that I can add is over here a paint node. Now paint node allows you to paint on top of an object. Now the same as before, if you want to activate it and you don't see anything over here, press enter, and like that you see this very small red dot. Now I'm going to increase the size of this, so I get something like this. Now again, you heard me talking in the past about using a pen for everything. Again, this shows also in programs such as this that a pen is really useful. So what we're gonna do is we're gonna make a red color, because what we want to have is we're gonna read out a value just from the red color only. Now I see there's another color being added over here, so I'll remove the value of what we have over here, so I have like pure red. And so now what I can do is I can start to paint over here and see what's going on. Well, it's not exactly what I had in mind. Let's undo this. The reason why is that my brush is also starting off very small. So the radius pressure, let's see, I think I need to make this one very small, so you get, okay, like this. So I can draw very soft and very hard. So what's being stored over here in an attribute, like I explained, in the colors of these points we have like red colors. Now what we can do over here, I've already split up this view, so let me do this for you again. So Alt square brackets, and let's change this view by clicking on the right mouse button over here, and let's go to the details view. So right now I see from this object that we have like a color attribute, CD, this color attribute added, and that each one of those points has like values, color values. So what we're gonna do right now is we're gonna read them in the copy node. Now what I want you to do is the following. We have over here $pt. Now I want you to find in the help file what the variable is for the red color channel and apply that. Now you will also see that if you apply it, that you probably are going to have like an issue that the objects are going to be so small that they're not going to be visible, or that there's a big chance that they're not going to be visible. So try to fix that as well. Okay, so let me show you the solution. If we go to the help file and we go over here to the local variables and we look then right here, diffuse point or vertex color. So color red, color green and color blue. So what we need is color red. So I'm gonna use this one again, dollar, and see, like I explained, first off it starts with red, it doesn't recognize it until it's completed, then it turns green. And so now we're reading out the red color and suddenly we don't see anything. Now what is the reason for that? Remember that in order to make sure that everything is visible, everything was being scaled to a very dramatic big size. And so we multiplied the results over here with this value. Now if we have these colors, the color values, they don't exceed the value of 1. So 1 is multiplied with this, so the maximum size that we're gonna get is 0.01. So just remove this and you will see that you have your boxes where you've painted them. So now I can go over here, I can still paint, and as you can see, you can just paint the boxes where you want to have them. Now I had a student in class saying, well, this is not really the optimal way, because if you look at this, let's click this node, you see all of these boxes are still being generated even when they're not being seen. They're so small that they're not seen, but you see all those points are being generated, so this is not a very efficient method. And that's true indeed. So what you can do is you can delete the points which are not usable. So think of it, what should you need in order to make sure that you have only the points that you need? You need to delete all the black points. Now how are we going to do it? Well, there are different ways how we can select the things that we need. First of all, let's find the entity. We want to remove the points that we don't need. And there are several things. Delete by pattern. Pattern is saying, for example, from 1 to 10. But this is not what we need exactly. So we're not going to use pattern. You can delete, for example, saying by range. If I show these points, so each 1 point out of 2 is going to be deleted as well. But again, this is not exactly what we need. So what we're going to do is over here, we're going to delete by an expression. Now expression, what it's going to do, it is going to delete the object when it returns a value of 1, or it's going to keep the object when it's returned a value of 0. So let's make an expression. If we type in $CR, so we take for each point the color red value, then we see automatically it is rounding this value, so everything which is about 0.5 is going to be deleted. Everything which is below 0.5 is going to be kept. Now this is not only the opposite of what we want, but this is also not very accurate, because we also want like the little bit smaller ones. And now if you see this as a result, you see on the end we still have like a few blocks, but that's not enough. That's not what we want. So what we can do is the following. If, let's say, the color red is equal to 0, then it's going to be deleted. So that means if the color red is equal to 0, then it's going to return true, which is 1. If the color red is not equal to 0, it's going to return you a value of 0, which is not being deleted. Okay, now you see over here this very special sign. Now these are Boolean operators, and you can find most of them probably on the wiki page. Let me give you some other examples. You have bigger than, you have smaller than, you have bigger or equal than, you have smaller or equal than. Then there are some other operations. For example, and, or, not, and so on. So look, try to find this, Google this, try to find this in wiki, and you will get an explanation, making sure that you understand. You can also find this in the help file. So try to find this where they are. So now we've deleted all the black points, the points which doesn't have like a proper size, and now we see we have these objects. So this is much more efficient because it has to make much less copies, much less evaluations, and it results into less geometry. Alright, so let's go back a little bit on what it is what we're doing, and with the stamp expression. So we saw that we've been playing with stamp expression, that we used this copy node in order to get from over here attributes and use them with the stamping over here. Now the thing which is important to know is that a copy node, when you stamp something, then the stamping expression can only work on nodes which are being used to be copied. So the stamping will allow you to make variations in the whole graph to be copied. That's very important to remember. The same counts for the for each loop. If you use a stamp expression, it's only going to work inside the for each, because it's evaluating the graph which is inside. So therefore it's only going to work inside. If you want to have like a stamping function working on this graph, for example, from this for each, that's never gonna work. If you want to have a stamping expression from this copy using over here, that's also not going to work. It needs to be a copied object. We talked about this randomness, talked about copying. Here are the elements that we've been using. So those are all the items we've covered right now in this whole list. Stacking boxes, using for loops, using the stamp function. I forgot to add using the copy nodes as well. But this gives you like the total overview of what we're doing. So the assignment is going to be a Greek temple. The floor plan is going to determine the placement of the columns. Yeah, you can read everything yourself. I'm just going to leave it over here. And you see all the things that you need to add. So take a good time to look at it. And this is more or less the most basic version of what you need to achieve. Something like this. And if you want, you can go much further. So this concludes the second lecture in procedural modeling.